Hi everyone, this is Mr. Cardoso, and here's the moment you've all been waiting for. I know you've been waiting for me to take up the reduce method, so let's get right to it. It's important to read the question when you're looking at this, so here it is on the right hand side. It says public void reduce, so it gives us the method header. It's void, the method is void, which means it doesn't return anything. So that should tell you if you wanted to do anything to your fraction, then it should reduce the implicit. So it's going to change the implicit values of the fraction into lowest terms. So for example, 16 over 24 can be reduced to 2 over 3, right? So here's the example of how it will be called. They even give that to you. So f dot reduce, that would go in your fraction calculator class, for example, where f is the name of your fraction in that class that you want to reduce. And so that becomes the implicit one. So let's go ahead and first of all, let's make an example. It's always great to work with an example. For example, we can even use, so let's say we have, f, and this is in our fraction calculator class, and that's why I'm using the blue color. So let's say I have, for example, 10 over 8, which is what I had, up here from the last question. So if I wanted to reduce 10 over 8, we know that the answer should be divide by 2 and you get 5, and divide by 2 and you get 4, right? So that's what we want in there when after this function call goes through, we want this 10 over 8 to change into 5 over 4. But for now, it's 10 over 8. So how do we get it into 5 over 4? So let's go ahead and start writing this method here. So we go public void reduce, open close brackets. Now, again, it doesn't need to take anything in because we are going to reduce the implicit fraction. So whichever is calling it. So first, let's start with now, of course, fractions can be negative. So you got to think about all these kind of strange cases, right? And if fractions are negative, so for example, you could have like a negative 3 over 2 or something like that. Well, that's already reduced, but that could mess with your algorithms. So what we're going to do is we're going to copy these into some variables. So let's go int posnum, which is the variable name for the positive numerator, and we're going to assign that the value of math.abs. Hopefully you remember that's the absolute value of the numerator. Or we can put num there, or we can put this dot num, either way. And so that makes it positive. And I'm going to go neg num. Sorry, that's not what I wanted to do. Pos den, mixed up those two things there. And I want to change the den into a positive version of itself. And that's not in camelback format, that's better. Now, notice that we are not changing, in these two statements, we are not changing the implicit fraction. What's left on the left-hand side of these equal signs here are two brand new variables that I've declared only within this method. So this dot num and this dot den currently, if this is our example here, 10 over 8, would remain 10 over 8. And this just makes them positive. So if it was negative 10 over 8, this would become 10 and this would become 8. So we're getting the positive values. Now, the reason why we're doing that is because we want to reduce. And to reduce, we're going to use a certain algorithm using a loop that's going to go through both numbers. So for example, this is the numerator, this is the denominator. So it makes sense to try to find the largest value that divides into both of these numbers. So the largest common factor, and then divide by the largest common factor. So we can start with either one of these two numbers. Let's say we start with 10, right? So we first check, is 10 divisible by 10? Yes, obviously, it's divisible by itself. But is 8 divisible by 10? No. So then we keep going. So let's check 9. Of course, 11 and 12 we're not going to check any of these because they're greater than the largest number here. In fact, 10 and 9 can't even be the greatest common factor between these two numbers. So the greatest common factor has to be the smaller number and below. So you can get this algorithm to be even more efficient by starting with the smaller of the two. But let's just skip that for now, and we'll pick either number, let's say the numerator, and we'll just go down from there. So, assuming the numerator most of the time is the smaller number. So 10 is not the answer, and so we're not even going to check these ones, 11 and 12, but 10 is not the answer. So we do check 10. It's not divisible. 8 is not divisible by 10. Neither is divisible by 9. Okay, what about 8? Well, 10 is not divisible by 8, but 8 is. But again, we need both of them to be divisible. So we keep going until we find one that is. 7 is not, 6 is not, 5 is not, 4 is not. 4 goes into 8, but it doesn't go into 10. 3 is not, and 2 is the answer. Okay, so why do we start from the top down? Because we want to find the largest common factor. If we started from 1 going up, yeah, 2 would be a factor, but we wouldn't be sure 100% if there wasn't a larger common factor. I mean, in this case, when you look at the example, it is, but when you're doing an algorithm, you're not exactly 100% sure. So that's why it's better to start from the top down. So, that being said, let's create our little for loop here. So I'm going to create a for loop that's going to start, so int I gets, let's say, pos new. So this is why we did that step with the absolute value, because if the numerator was negative, then this would get really messed up, right? Our algorithm would fail at that case. So you have to look at these loopholes or test it out, and then maybe you'll see that that's the reason why it's not working. And so we're going to start I at the positive numerator. So let's say in this case it would be 10. And then we're going to say I is greater than 0. So we're going to go all the way down to 1, because 1 might be the GCF. And if that's the case, then basically it's already reduced. And so 1 is the smallest number we'll check, and then, or we can even go to 2, that's fine. And because it's greater than 0, so we're not checking 0, we're not trying to divide by 0. And then I minus minus. So we're going down, again, like I said there. Open that up. Now, inside, what did we do each time? So in this case, we're checking 10 first. I is going to be 10. So, we write an if statement, and we say if, so we want to check if the numerator is divisible by, so we can say if pos num mod I equals 0. So that's checking to see if I is a factor of the numerator. And if you get a modulo, if you modulo and get a remainder of 0, then that means it's a factor. Okay. And we also need it, so that means the positive, I is a factor of the positive, the numerator, and we also want to check if I is a factor of the denominator. So pos den mod I equals 0. And in this case, you could actually use num, this dot num and this dot den here, or pos num and pos den will give you the same answer. The only thing that we would really require to use it here is this one, because that would, if that was negative, that would really mess up your loop. Now, if that's the case, that means that this I is the largest possible, because we started from the highest possible value and we're going down. So that means that I is the largest possible common factor if both of these are true. Right? So if we're in this if statement, that means that I is the GCF, greatest common factor. So that what do we want to do? Well, we want to go, now this is where we actually change the numerator and denominator. So I can say divide equals for shortcut if you're having trouble with that. I'll go this dot num is equal to this dot num, divided by I. And you don't have to worry about integer division. We already know that I is a factor of the numerator because it passed this test. And we know that I is a factor of the denominator. So this dot den is equal to this dot den divided by I. So basically what we're doing here is we're taking the numerator and dividing it by the GCF, and we're taking the denominator and dividing by GCF, and we're putting it back in to the same numerator and denominator field, thereby modifying the implicit fraction. So this is why, again, we don't have to return anything, because these two are being changed inside right here. Now, once that's complete, should we, let's say, for example, I know 8 is not a factor of the GCF, but let's say it was. Let's say 8 was the GCF of 10 and 8, just for example. Do we need to check and continue checking? We could, but we don't want to do that because then this division will take place, and we already found it, it'll be inefficient. So once you're finished with this, you found the GCF because you're starting from the biggest going down to the smallest. So at this time, you can just type return semicolon. And what that will do is basically says, you found the GCF, you've divided both by the GCF, which means you've reduced it, and so you can return because you're done, right? And so that will get you out of that loop as well as return you from the method. You can break as well because there's nothing after this loop. So break will work just the exact same way, but return will return the method like right away and return to the caller. Okay, so let's compile that, make sure it compiles, and it does. So now how this works is, let's say we make another fraction. I'm just going to make a brand new fraction here. So fraction, let's say f gets new fraction. Okay, and then I can go f dot new gets 10, and f dot den gets 8. Now how I would call this is I would go f dot reduce. So I can say, let's leave that one in there. Let's take this one out. My fraction is f. Okay, so let's compile that, and let's run it. Oh, I forgot to take the comment out. And we get 5 over 4. So our fraction f, so just a demonstration again of how this works. I keep repeating this just to make sure it drills in your head. The fraction f is pointing here. It exists in this class, in the fraction calculator class, f. Right, but it doesn't exist in the fraction class. So we set the values to 10 over 8 as we have here. 10 over 8, so we've done that here. And then we say f dot reduce. So again, f becomes the implicit fraction because it's the one before the dot. It calls the reduce method. It looks for reduce because f is a fraction, right? F is a fraction. It looks for the reduce method in the fraction class. It finds this method. It notices that it's void. It runs all of this and reduces it and then returns, but it doesn't return anything because it's a void method. So what's actually changing is, like I said before, when f is passed into the fraction class, the pointer here is this. So this dot num and this dot den is basically like writing f dot num and f dot den at this moment because it's pointing at f. And so it'll change those values and then return back saying I'm done. As soon as it finds it, it's done, and it'll come back here, and that would have changed these values. So it would change these values to 5 and 4 within the fraction class, then hit return, and this would have changed. F would have changed because f and this are pointing at the same fraction. I hope that makes sense how the reduce method works. There are other things that you can do to make the reduce a little bit better. You can even put the reduce right into your toString. So for example, you could call this dot reduce before. That should be a point.